In this video, I am going to explain how to express symmetry operators by permutation of atom levels. I will take the example of Allene molecule, this one. Its structure is like this. One part is in one plane and the other part is on a perpendicular plane, and the point group is D to D. I explained all these in my earlier video. Now it is convenient to use this diagram for the structure. It is a rectangular box. The three carbon atoms are placed linearly at the center of the box, and the hydrogen atoms occupy alternate corners of the box. This will be the structure. These are the CH bonds, and this is the structure of Allene molecule. Now, how to express any symmetry operator by using these atom labels? The hydrogen atoms have been labeled as 1, 2, 3, and 4. Labeling these atoms is not necessary for the present purpose. A symmetry operator R can be expressed in this way. This is a bracket. In the first row, we are writing the atom levels 1, 2, 3, and 4. And in the second row, the new levels, new positions of the atoms will be written down here after carrying out the symmetry operator. Suppose by carrying out R, 1 comes to the position of 3. Then we will write 3 under 1. In this way, this row is to be filled up. And this will be a permutational representation of the symmetry operator R. For example, in this diagram, identity operator is expressed like this. 1, 2, 3, 4, and then again 1, 2, because nothing is changed by identity operator. 1 remains here, 2 remains here, 1 at its own place, 2 at its own, and so on. So this is the permutational representation of identity operator. And what about the C2 operator? C2 is a line passing through the center of this face and center of this face and passing through the three carbon atoms. This is the principal C2 axis. If we rotate the box, 1 will come to 4 and 4 will go to 1. Similarly, 2 goes to 3 and 3 goes to 2. Therefore, the C2 operator is written in this way. C2 is 1, 2, 3, 4. These are the initial levels. Now 1 goes to 4 by a C2 operator. So 1 goes to 4, 2 goes to 3, 2 goes to 3, and 3 goes to 2, 3 goes to 2, and 4 goes to 1. So this is the permutational representation of C2 operator. In the same way, we can show the other operators. For example, let us carry out C2 primed operation. C2 primed operation. The initial position is like this. This is the initial configuration. The C2 primed axis is passing through the center of the front face and going out through the center of the back face. If we carry out a C2 primed, this is C2 primed because this is perpendicular to the principal C2 axis. And this is C2 primed 1 because there is another C2 primed axis perpendicular to the same principal axis. Now, if we rotate this box about this axis, what will happen? This face will come over to this face. So, this front face will remain the front face because it is passing through the center, and the back face will remain the back face. Therefore, in the front face, 2 and 4 will exchange places, and in the back face, 1 and 3 will exchange places by rotation. Therefore, what will be the permutational operator? 1, 2, 3, 4. we are turning this face. So 4 goes to 2 and 2 goes to 4. 2 and 4 exchange places. 2 and 4. 2 goes to 4 and 4 goes to 2. Similarly here on this face, 1 goes to 3 and 3 goes to 1. 1 and 3 exchange places. So this is the permutational representation of C2 1 primed operator. Similarly, we can construct C2 2 primed operator. This is done here. This is done here. C2 2 primed operator is like this. And if you rotate the box, what will happen? This face and this face will not change. Only the atoms will exchange places. So 1 and 2 will exchange places. Similarly, 4 and 3 will exchange places. So this will be the permutational representation of C2 primed 2 operator. Next, let us consider a dihedral symmetry plane. This is sigma D1. This consists of this symmetry plane. Now, what will happen if we carry out a sigma D1 operation? Sigma D1 operation, this is sigma D1 plane because there is another such plane. What will happen? We see that 2 and 3 are on the plane of symmetry. Therefore, they will not change their places. 2 will remain here, 3 will remain here. And what about 1 and 4? 1 by reflection comes here and 4 goes there. So the permutational representation will be 1, 2, 3, 4. Then 1 goes to 4. 1 goes to 4. 2 remains at 2. 3 remains at 3. And 4 goes to 1. 4 goes to 1. This is sigma D1 operator expressed in the form of a permutation. Similarly, sigma D2 is another dihedral plane. It is like this. It consists of this and these two diagonals. This is the sigma D2 plane, and by the same manner we have constructed the permutation for this operator. And now we are left with the S4 operator, improper rotation. Improper rotation, the initial configuration is like this. Now, using this axis, we rotate the box through an angle of 90 degree. Instead of C2, we are carrying out a C4 operation. Although C4 actually does not exist, but we are using this line as a C4 axis. Then what will happen? This by 90 degree rotation 1 will come here. By 180 rotation 1 comes to 4. Then by 90 degree rotation 1 will come here. Vertex 1 will come here. 4 will go to this place. Because this plane cannot change. Similarly here, this plane cannot change. 2 will come to this position. 2 comes here. And 3 goes to this position. And clearly, this is not equivalent. This is not equivalent to the initial configuration. So this is not a symmetry operation. But now we carry out a perpendicular reflection on a perpendicular plane. Perpendicular to this axis, we imagine a mirror plane like this. Then what will happen? 3 will be reflected to this position. 3 comes here. 1 comes here. Then 2 goes to this place. 2 and 4 from here comes to this place. This is 4. We now see that these two are equivalent. Therefore, this whole operation C4 followed by a sigma perpendicular operation is a symmetry operation, and we call it S4. And what is the permutational representation for this S4 operation? 1, 2, 3, 4. Then 1 goes to 3. 1 goes to 3. 2 goes to 1. 2 goes to 1. 3 goes to 4. And 4 goes to 2. So 3, 1, 4, 2. This is the permutational representation of S4. And in the same way, we can carry out S43 operation. S43 is like this. About the same axis, we have to rotate it through an angle of 270 degree. By 90 degree rotation, it comes here, 90, then 180, then 270. 1 will come here at this place. Similarly, 4, 90, 180, 270. 4 will come here. In this way, this diagram has been drawn, and then using a perpendicular plane, we have arrived at this configuration. We see that this is also a symmetry operation. This is a C4 3 rotation, and therefore this entire operation is S4 3. S4 3. And now looking at the vertex levels, we see that the permutation is 2, 4, 2, 4, 1, 3. This is the permutational representation for the S4 3 operation. Now I will show an example of symmetry multiplication using these permutations. I have collected all the permutations here. All the permutations here. Now let us suppose we want to carry out this symmetry product. C21 primed and then sigma D2. So we have to write this, the permutation for this C21 primed. This is written here on the right. 3, 4, 1, 2. 3, 4, 1, 2. And then for sigma D1, we have to write 4, 2, 3, 1. 4, 2, 3, 1. What will be the product? We see that the initial labels are to be written first. Now here the procedure is from right to left. This operation is to be carried out first. So we see here that 1 goes to 3, and then here 3 goes to 3. 1 goes to 3 and then 3 goes to 3. Therefore 1 finally goes to 3. Similarly 2 goes to 4, and here 4 goes to 1. 2 goes to 4 and then 4 goes to 1. Therefore 2 finally goes to 1. 3 goes to 1, and here 1 goes to 4. Therefore 3 goes to 4. And 4 goes to 2, and here also 2 goes to 2. 4 goes to 2, then 2 goes to 2. Therefore 4 finally goes to 2. So this 3, 1, 4, 2, this is the result of this product. And what is this? This has to be present in this list because of closure property. We see that this is here. 3, 1, 4, 2 is S4. So this symmetry product is S4. S4. In this way, all the symmetry products can be carried out, found out, and the entire symmetry multiplication table and even all similarity transformations can be carried out using such permutations. If this list of permutations is ready at your hand, then the other tasks will be very easy. This is what I wanted to explain today. Let me thank you for watching the video.